Section: Introduction. In this section, we will discuss how large language models, LLMs, have shown impressive abilities across various natural language tasks. Typically, during LLM training, documents are randomly selected, and each document is used only once for an update step without repetition. This differs from how humans learn, where information is structured over time and often repeated to maximize learning. To mimic this natural learning process, we investigate a training setup where documents are presented cyclically in a fixed sequence and repeated multiple times. In traditional training, networks often struggle with catastrophic interference, where learning new information leads to forgetting previous knowledge. Surprisingly, in our structured training setup, LLMs exhibit anticipatory recovery behavior. They recover forgotten information before revisiting it in the sequence, similar to anticipating breakfast while showering in the morning. This behavior emerges without explicit memory storage or content overlap across documents. Through extensive experiments, we explore how model architecture and training methods influence this anticipatory recovery phenomenon. We provide insights into training dynamics with structured input data and propose hypotheses for this behavior. While this phenomenon is not unique to LLMs, vision models with adequate size also show similar behavior. However, LLMs excel in language tasks with the strongest recovery effect. Moving on to the data and experiment setup, we utilize the Pythia suite of decoder-only autoregressive language models trained on the CNN, Daily Mail News dataset. The dataset, originally for text summarization, is repurposed for causal language modeling by using only the articles for training. We focus on studying memory retention for specific documents within the training history rather than generalization to new data. Our training setup involves sampling a set number of documents, truncating them to a fixed length, and fine-tuning the language model for multiple gradient steps on each document. We refer to this process as an episode. After each episode, we evaluate the loss on all documents and repeat the training for a set number of epochs. We use standard hyperparameters and the average cross-entropy loss as our evaluation metric across multiple trials to ensure robustness in our findings. Section Summary. In this section, we investigate a more naturalistic training approach for large language models, LLMs, by cyclically presenting documents in a fixed sequence, allowing for repeated exposure and multiple gradient steps per document. Surprisingly, LLMs exhibit anticipatory recovery behavior, recovering knowledge from previous documents before encountering them again, even without explicit memory or systematic content overlap. This phenomenon is more pronounced in larger networks and is not unique to LLMs, as some vision models also demonstrate similar behavior under certain conditions. Section: Emergent Anticipatory Recovery. In this section, we will share our findings from the experiments we conducted to uncover the anticipatory recovery phenomenon in large language models during cyclic fine-tuning. We will show that anticipatory recovery only occurs in models with enough capacity. In our first experiment, we worked with 25 documents and performed cyclic fine-tuning on them for 5 epochs in the same random order. Even though the documents and order were chosen randomly at the beginning and remained fixed during fine-tuning, we noticed something interesting. Initially, when we fine-tuned on document 1 for 10 steps, the model's loss on that document decreased significantly. However, as we fine-tuned on other documents and then returned to document 1, we saw that the model's loss on document 1 increased due to interference. Surprisingly, as we cycled through the documents again, the loss on document 1 started to decrease around the 15th document and continued to decrease before we returned to document 1. This unexpected decrease in loss is what we call the anticipatory recovery phenomenon. To quantify the anticipatory recovery phenomenon, we introduced a recovery score, which measures how much of the initial forgetting the model recovers before revisiting the same document. We calculated this score based on the maximum loss on each document before and after training on it. We then explored how different model sizes and training parameters affect anticipatory recovery. By conducting experiments with Pythia models of various sizes, such as 160M, 410M, 1B, and 2.8B, we found that larger models exhibit stronger anticipatory recovery. This indicates that anticipatory recovery is an emergent behavior dependent on model size. Next, we investigated whether anticipatory recovery is influenced by pre-training by repeating the experiments on randomly initialized models of different sizes. We observed that even in randomly initialized models, anticipatory recovery exists, although it is not as pronounced as in pre-trained models. The trend of larger models showing stronger recovery still held true. Furthermore, we examined the impact of model width and depth on anticipatory recovery by varying these parameters in a Pythia 1b model. Our results showed that the model requires sufficient width, at least 512, and depth, at least 8 transformer blocks, to exhibit noticeable recovery, confirming that anticipatory recovery is an emergent behavior linked to model size. Section Summary. In this section, we present our experimental findings on anticipatory recovery in large language models through cyclic fine-tuning. We show that this phenomenon emerges only in models with adequate capacity, where the model's loss on documents decreases and then unexpectedly recovers during sequential fine-tuning, even before revisiting the same document. This behavior is quantified by a recovery score and is observed to be stronger in larger models, indicating that anticipatory recovery is an emergent behavior dependent on model size. Section: Other influential factors. In this section, we discuss the impact of various training hyperparameters on the anticipatory recovery phenomenon. We explore how changing different factors in the training setup affects the average loss curves when cyclically fine-tuning a pre-trained Pythia 1b model. We also present additional results in the appendix. Firstly, we investigate the effect of increasing the number of tasks, T, the model is fine-tuned on in each epoch. We vary T from 10 to 200 and plot the loss curves. We observe clear recovery for all curves, indicating that the model can remember a task transition even after training on 200 other tasks. Next, we analyze the impact of the number of gradient steps, M, taken on each task. Increasing the number of gradient steps generally leads to a higher recovery score. We show that even with just one gradient step, there is still some anticipation if a larger learning rate is used. We then experiment with different context lengths, C, and observe that a larger context length is associated with a lower recovery score. This suggests that more gradient descent steps are needed to memorize the task with a longer input context. Furthermore, we explore the effect of freezing a subset of transformer blocks in the pre-trained model during fine-tuning. Results indicate that at least 8 tunable transformer blocks are needed to observe a strong anticipation phenomenon in the last epoch. Additionally, we compare the performance of the Atom optimizer with standard gradient descent. Atom facilitates anticipatory recovery by producing greater initial forgetting, resulting in a higher average recovery score compared to vanilla gradient descent. Moreover, we investigate the impact of data randomness on anticipatory recovery. We find that while the phenomenon is weaker with more variation in each data point, it still exists. Overall, our experiments suggest that the model's ability to adapt to each task is crucial for anticipatory recovery. Factors such as a larger number of gradient steps, shorter context length, more learnable layers, and a better optimizer contribute to a higher recovery score. Lastly, we explore the anticipatory recovery phenomenon in computer vision tasks, such as causal image modeling and image classification, to assess its generality. Additional details on the experiment setup can be found in the appendix. Section Summary. Other influential factors. In this section, we investigate how various training hyperparameters impact the anticipatory recovery phenomenon. By adjusting factors like the number of tasks, gradient steps, context length, frozen blocks, and optimizer type, we observe that a model's ability to adapt to each task significantly influences anticipatory recovery. Additionally, introducing data randomness during training reveals that while more variation in data points weakens the recovery effect, it still remains present. Section: Causal image modeling. In this section, We utilize pre-trained models for both image and language tasks to investigate the phenomenon of anticipatory recovery. We fine-tune our models on specific datasets and observe the loss curves to analyze the training dynamics. Our experiments reveal that anticipatory recovery occurs not only in language modeling but also in image classification tasks using various models. To delve deeper into the dynamics of anticipatory recovery, we explore whether it stems from causal mechanisms or simply from similarities between adjacent tasks learned by the model. By conducting experiments where we reverse the task sequence, we find initial evidence supporting the latter hypothesis. We further investigate the relationships between tasks and analyze the model's gradients, weights, and activations across training history to gain insights into cyclic training dynamics. Our exploration begins by examining the similarities in gradient information between documents during training. We focus on the gradient vectors at a specific transformer block and observe the cosine similarities between them. Surprisingly, we find that the gradient similarities peak not along the diagonal as expected, but near the center of the heat map. This suggests that the strength of facilitation between documents depends on the position in the training cycle, adding a new dimension to the anticipatory recovery phenomenon. By analyzing pairwise loss recoveries between documents at different points in the training cycle, we confirm that the recovery is most significant when the model is fine-tuned on proximal documents. The symmetric nature of the pairwise loss recovery matrix indicates task symmetry, where updates on one document affect the loss of nearby documents. This finding provides valuable insights into the dynamics of cyclic training and the anticipatory recovery phenomenon. Section Summary. In this section, we explore causal image modeling using pre-trained models on CIFAR-10 for fine-tuning and observe anticipatory recovery in cyclic training for both image and language modeling tasks. By experimenting with VIT and VGG19 models on ImageNet, we confirm anticipatory recovery in image classification models as well. We investigate the dynamics of cyclic training and find that the recovery strength between documents depends on the training sequence, suggesting a correlation between tasks rather than a causal mechanism. Section: Temporal structure of model weights. In this section, we examine the temporal structure of model weights. We investigate how the weights of our model change during cyclic training. Initially, when we compare the raw weight vectors of the model at different points in the training process, we notice that they are very similar to each other. This is because the weights are close together along the training path and the weight vector is large with a few dominant entries, causing numerical instability. To address this, we look at the weight residuals instead. By calculating the difference between the current weight and the average weight in a window centered around the current point, we can focus on the updates specific to each document. Visualizing the cosine similarity between these weight residuals reveals a cyclic pattern that aligns with the training epochs, indicating similarity between weight updates for nearby documents. Additionally, we explore using principal component analysis, PCA, to reduce the dimensionality of the weights. By analyzing the top three principal components of the last layer weight vector, we observe a helical structure in the trajectory. This helix seems to aid in anticipatory recovery, where the model adjusts its weights to anticipate revisiting a task, leading to better performance on all tasks over time. The helical structure is not a guaranteed outcome of cyclic training but plays a crucial role in anticipatory recovery. Moving on to the temporal structure of activations, we visualize how the activations of a single document evolve during cyclic training. We observe a blocked pattern where the similarity between activations increases across each epoch, suggesting that the model's internal representation of a document becomes more resistant to changes from updates on other documents as training progresses. To gain further insights into anticipatory recovery, we create a simplified simulation experiment. Each task is represented by a data point, and we use linear embeddings and task-specific mappings to model the learning process. By sequentially optimizing each task and updating the model parameters accordingly, we observe a gradual formation of a circular pattern in the model's representations of all tasks. This aligns with the concept of anticipatory recovery, where adjusting the model's parameters leads to improved performance on upcoming tasks. The experiment results show that larger networks can facilitate anticipatory recovery by quickly adapting to new tasks and mapping task features closer together. The analysis confirms that the model's representations organize into a cyclic structure over time, supporting the effectiveness of anticipatory recovery in improving task performance. Section Summary. In this section, we investigate the temporal structure of model weights during cyclic training by exploring weight residuals to focus on model weight updates for each document. By visualizing the cosine similarities between weight residuals, we observe a cyclic structure aligning with training epochs, aiding in anticipatory recovery and reduced forgetting. Additionally, we use principal component analysis, PCA, to reduce weight dimensionality, revealing a helical trajectory that gradually converges, essential for anticipatory recovery and achieving low loss on all tasks during cyclic training. Section Summary. In this section, we visualize the changes in model weights using heat maps and displayed model activations and gradients during cyclic training. We discussed the unique temporal patterns observed in these heat maps. We also graphed the recovery degree when fine-tuning on one document and evaluating on another, along with the evolution of model weights across different tasks. Our findings indicate that once we train on a document, the model's understanding of that document becomes less affected by updates from other documents. Additionally, we presented a simple experiment illustrating a similar anticipatory recovery pattern in the loss curve and linked it to neural network training dynamics involving task-specific and task-general parameters. These results provide insights into the dynamics of cyclic training. In related work, prior studies have examined convergence rates in training scenarios where data points are shuffled once and that order is maintained for all epochs. Our research focuses on cyclic training and explores how the loss changes for each task throughout the training cycle, revealing the anticipatory recovery effect. We also extend this analysis to include multiple gradient update steps per data point. While our study simplifies the training setup compared to other works, we aim to uncover more about applying standard SGD on highly parameterized networks. Future research could delve into anticipatory recovery in environments with complex hierarchical sequence structures. Online learning involves tasks presented in a sequential stream. Our research on cyclic training can be seen as a special case of online learning with a cyclic data repetition structure. By employing multiple online gradient descent steps on each document in the stream, we investigate the training dynamics of over-parameterized neural networks. Recent advancements in large-scale transformer networks have showcased their ability to model long sequences of language data effectively. Our work explores the sequential learning setting with cyclic task repetition and reveals task anticipation as a new emergent capability of large models. Traditionally, neural networks are trained for a single task, and transitioning between tasks can lead to catastrophic interference, causing a drop in performance on previously learned tasks. Continual learning addresses this issue by sequentially learning tasks without forgetting. Our research focuses on sequential learning environments with cyclic repetition, extending interleaved training to multiple tasks and uncovering the anticipatory recovery phenomenon. This finding contributes to understanding how large networks can avoid catastrophic interference. In our study, we investigated the training dynamics of over-parameterized neural networks, particularly LLMs, in sequential cyclic fine-tuning. We discovered the phenomenon of anticipatory recovery, where networks recover from initial forgetting before revisiting the same document. This effect occurs when the network has sufficient width and depth and is well fitted to each document before moving on. Factors like the optimizer also influence the degree of recovery. Visualizations of model weights, activations, and gradients reveal a clear temporal structure, providing insights into anticipatory recovery mechanisms. Further research is needed to explore the mathematical basis of anticipatory recovery and why it is more pronounced in LLMs for autoregressive tasks. Our study on cyclic training differs from traditional machine learning setups, considering task repetition and switching costs, which are crucial for real-world learning experiences. Future investigations could explore neural network training dynamics in diverse structured environments from both theoretical and empirical perspectives. Developing effective learning curricula to balance learning efficiency and task switching costs is a promising direction for more naturalistic training setups. Additionally, rethinking continual learning algorithms in the context of LLMs to leverage their sequential memorization capability could lead to significant advancements in modeling. Section Summary. In this section, we visualized model weight dynamics with heat maps and explored model activations and gradients during cyclic training. We observed a special temporal structure in these heat maps and found that the model's representation of a document becomes less sensitive to gradient updates on other documents after training on it. Our results suggest an anticipatory recovery phenomenon in cyclic training, shedding light on the dynamics of training over parameterized neural networks. Section: Acknowledgement. In this section, we express our gratitude to the NYU Agentic Learning AI Lab members for their valuable discussions. Our computational work was made possible with the support of the NYU high-performance computing resources, services, and staff knowledge.